linear system. So that means because every linear system of equations, it is just we are writing actually in matrix form x equal to b. So ultimately we are just dealing with matrices. So two system of linear equations are said to be equivalent if they have same solution set. So now let me tell you what is the meaning of solution set. So for any, whatever the example we just discussed here, these are non-trivial solution and trivial solution. These systems have simply unique solution. But what is the meaning of solution set? Solution set means set of all the, you can say, set of all, suppose we are considering two variable and two equation system of linear equation. Then so that means a solution set means what? All the order pair which satisfy these two equations, these two equations. That is called the solution set. So for example, in this case, if I ask that what is the solution set, so that is nothing but so for this actually solution set is nothing but, so this is set first of all. So here we have only one pair, so 0, 1. This is the solution set. And for this system of linear equation, solution set is, because there is only one solution. But it is not all the time case that a system will have simply unique solution. A system may have no solution or maybe infinite solution. For example, so if you just consider the two linear system, this is one system of linear equation, and second one you take then if you see the first system of linear equation, then you can see that this is this is called a redundant system, because there is only second equation is similar to first equation. So ultimately there is only one equation, that is x plus 2y is equal to 1. So this system is actually redundant to the system, or we can say simply one equation, x plus 2y is equal to 1, right? So solution for this system of linear equation means set of all order pair which satisfy this equation simply, because this system actually nothing but just simply this one equation, x plus 2y is equal to 1. So there are infinitely many order pairs x comma y which satisfy this equation, because this is what? This is just line. So all the points which are lying on this line are the solution for this system of linear equation. In fact, in this case, if I write complete solution set or simply solution set, so that will be actually, so you can see for any value, if you give any value for x, then y value we can find from here. So that means any solution of this form c comma 1 minus c by 2, where c is any real number. So this is the complete solution set for the system 1, because any order pair of this form c comma 1 minus c divided by 2, where c is any real number, that will be the solution for the system 1. So that is the basically, so there are, c is arbitrary, so there are infinitely many real number. So you can choose any real number, then the corresponding order pair will be the solution for the system 1. So this is the complete solution set for system 1. Whereas if you just look at the system second, so you can see that and in fact you have studied this type of system of linear equation. So these are the representing two parallel lines, right? So and they are never going to basically intersect. So therefore solution set for this system second is nothing but simply empty set phi. So a solution, I mean a system of linear equation may have no solution, may have infinite solution, may have unique solution. So all these three things we have discussed here. So what is the meaning of equivalent? So first linear system is 2x plus y is equal to 1. 4x plus y is equal to 1. This is one linear system of equation. And another linear system of equation is 6x plus 2y is equal to 1. Sorry, 2. And 4x plus 2y is equal to 2. So what we can see here that both the system are look like very different, right? Because a system of linear equation is just determined by the coefficient matrix and that B, or in simply we can say that a system of linear equation is just determined by this augmenting matrix. If you know this augmented matrix, then you know the system of linear equation, the corresponding system of linear equation, and vice versa. So these are the two different system of linear equation. But what we can see here, the solution set for both the system are simply same, because for first system solution set is simply this order pair 0, 1. And also you can see for the solution set for the second system, that is also 0, 1. That means only one solution. So both the systems are very different, but both have same solution set. So such type system of linear equations actually called the equivalent system. So here system 1 and 2 are equivalent. Because both have same solution set. Now let's see basically what is the advantage of equivalent system. This is just basically illustration of what is what are the equivalent systems. But what is the advantage of equivalent system actually? So the thing is that sometime suppose this is just a two variable case, but we may have a system of linear equation in four equation with five variables or something, any order. That means any we may have any order matrix A. So in that case, always what we want actually, that we want a simple system of linear equation. So what is the meaning of simple system of linear equation or easy system of linear equation? So easy in the sense that they can be solved easily. So for example, if suppose you have this type system of linear equation, 2x1 plus x2 plus x3 plus x4 is equal to 1, x2 plus 3x3 plus x4 is equal to 2, and x3 plus 4x4 is equal to 4. And so suppose we have this type system of linear equation is given, then these systems are basically easier to solve or to find the system to solution for this type system of linear equation, because the reason is very simple. Here also basically in this case, of course, we will not get unique solution, but what is the advantage here, that you can find the solution for this type system linear equation using the back substitution. So now what is the meaning of back substitution? So basically back substitution is the process in which we start uh, solving equation in the backward direction. That means first we find the value of a variable from the last equation, and then whatever the value we find from the last equation, that value or we put in the just previous equation, and this way we move backward. So for example, for this system of linear equation, what we'll do, we will first of all, this system basically doesn't have a unique solution. So that means we will take x for any real value, or you can say that x3 just put here 4 minus 4x4, and then this value we will put here. So we will get x2 in terms of x4, and simple is in the same way, after that we will put x2 and x3 value in the first equation. Then we will get the x1 in terms of x4. So that means what? When we have these type system of linear equation, then you can just solve these type system linear equation using the back substitution. So these are the basically special types of system of linear equation. Also, if you have system of linear equation in which our matrix is simply diagonal matrix. Okay, so if the matrix is simply diagonal matrix, in that case, that is more easier than this system of linear equation. So that means suppose the given system of linear equation of this form. That means suppose we have 2 0 0 0 4 0 0 0 3 0 0 0 and 1. x1, x2, x3, x4. So suppose we have these type system of linear equation. A matrix has, this is our basically A matrix, right? So this matrix, it is just diagonal matrix. So what is the advantage of these type of diagonal matrices? If we have these type diagonal matrices or these type linear system of equation, then we can find basically solution of this system easily. Just you can see what will be the solution. Solution will be So solution. So basically, what is this system of being equation? So this will become actually 2x1 is equal to just 1, because need to apply R2 is replaced by R2 minus 2R1, and R2 R3, I mean R3 is replaced by R3 minus 2R1. So then we will get equivalent matrix here. So matrix will be 1, 1, 1, and this is 5. So first row is same. Now in the second row, it will become, of course, 0, 0. And now this one. So 1 minus 2. So this will become minus 1. And this is minus 1 and minus 2. So that means that will become minus 3. And this one is 2 minus 5 times 2. So that means 2 minus 10. So that is minus 8. And last row, minus 1 and minus 2. That means minus 3. And 1 minus 2, that is minus 1. And 2 minus 10 again, so that is minus 8. Now this is the basically row equivalent matrix we are obtaining. So next step is just look at the second row and then see what is the first non-zero entry, and if it is not 1, then make it 1, just applying the appropriate elementary operation, and make all the entry below, which lies below to that first non-zero entry in the second row, just make the 0. So that means first of all we will make this is entry 1. So for that we will apply R2 is replaced by R2 minus 1 R2, right? So we will get equivalent matrix H 1, 1, 1, augmentation bar 5, and then so this is 0, this is plus 1, this is plus 3, and this is plus 8. And last row, of course, same. Next, now in the second row, first non-zero entry is 1. Now next thing, we have to make this entry minus 3 0. So for that we will apply elementary operation. R3 is replaced by R3 plus 3R2. So first row is same, 1, 1, 1.
सर R1 नहीं हो सकता?
Sorry?
3R2 की जगह 3R1 नहीं हो सकता?
If you will take 3R1, then what will happen? This entry is already 0. So at this place you will get 1 here, but that we don't want, right?
Okay. Thank you.
So the first row is 1, 1, 1. I'm not saying that you can apply elementary row operation in any order. But the thing is that ultimately we are trying to find the row echelon form. So all these things you have to remember in that what are the conditions for row echelon form. So that way you have to apply the elementary row operations. That's it. So in the second row now, after applying this elementary row operation, R3 is replaced by R3 plus 3R2. What will get? 0, 1, 3. So this second row will remain same. And the third row is 0. And then you are applying this elementary operation. So of course you will get 0 here. And then minus 1 plus 9 actually. So minus 1 plus 9 means plus 8. And then at this place minus 8 plus 8 times 3. So this is 24 minus 8. That means 16. Okay, so now next thing is look at the third row and then see what is the first non-zero entry in the third row and then make it 1. And of course, this is the final row. So we don't need to say anything about them, make the entry 0 below of this entry, no first non-zero entry. So that is the final row. There is no entry which is below of it. So now only thing is we need to make it 1. R3 is replaced by 1 by 8 R3. So after applying this elementary operation, the equivalent matrix will be 1, 1, 1. Just 1 minute. This is 1, 1, and this is 0, 1, 3, 5, 8. This is 0 and 0, and this is 1 and this is 2. So this is the our basically final. I mean, this is the basically required row echelon form of the given matrix, right? Because this is satisfying all the property. So this is the row echelon form of what? Matrix, this augmenting matrix, A augmentation bar B. Not also basically, of course, this is also row echelon form for the matrix A as well. So which is the row echelon form, and that exactly we call actually C augmentation bar D. So you can see this is our C augmentation bar D, and that times just we are basically assuming now.
Shouldn't we change the 3 also?
Sorry. Oh, basically in the second step only there is difference. So in this case, basically what we'll do, we reduce this given matrix into reduces row echelon form. After that, everything is same. In fact, of course, this last step will not be required, because when we reduce some matrix into row echelon form, in the reduces row echelon form, in the most of the cases, basically we will get simply diagonal matrix. I'm not saying all the time, but most of the cases we get actually diagonal matrix. So of course, in that case, it's back substitution procedure is not required. But if we do not get actually this diagonal matrix in the reduces row echelon form for the matrix A, then also the step same. That means you just apply the back substitution to get the solution for the corresponding system. Cx equal to d, and that will be exactly the solution for the given system of linear equation. So this is what the one difference between Gauss elimination method and Gauss Jordan method. So now let's see some example to get the better understanding. So now let me take one example. So system of linear equations is given here. Solve the following system using Gauss elimination method. So what is the system of linear equation is given here. So this is the system of linear equation. X1 plus X2 plus X3 is equal to 5. 2x1 plus x2 minus x3 is equal to 2. 2x1 minus x2 plus x3 is equal to 2. So this is the system of linear equation is given. So now let's see how we apply the Gauss elimination method. So in the Gauss elimination method, first step is we need to construct the augmenting matrix. So first of all, you can see in matrix form, given system of linear equation, we can write in matrix form. So matrix form, if I write here, then that means Ax equal to B. So now see what are the A, X, and B. So A is equal to coefficient matrix, that means 1, 1, 1, 2, 1, minus 1, 2, minus 1, and 1. This is the A matrix, and X matrix is x1, x2, x3, and B matrix is the right hand side matrix, that means 5, 2, and 2. So we have A and we have B, so that means we can write augmenting matrix. So the augmenting matrix of system 1 is A, this is the notation, and also one thing I will tell you here, that sometimes we use the basically dashed line, or I mean some books actually we use the dashed line for augmentation bar, and in some book we use the solid line. So in this book basically we will use the solid line for the augmentation bar. One, 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 2, 1, minus 1, 2, minus 1, and 1. Then augmentation bar, then B matrix, that means 5, 2, and 2. Okay, so this is the first step of Gauss elimination method. So next we will reduce this matrix, augment matrix, to the row echelon form. So now Gauss-Jordan method. This is also called row reduction method. So these are the two methods solving a system of linear equation Ax equal to b, and both the basically method are based on this theorem particular. So basically, what is the simple procedure for both the methods? So let me just tell you what is the Gauss elimination method. So in Gauss elimination method, suppose we have the given system of linear equation Ax equal to b. So suppose we have and we want to solve this system of linear equation. So in that case, in Gauss elimination method, what we do, we first of all construct this augmenting matrix. So I'm just in brief, I'm writing the steps. So that means, first of all, we need to construct augment matrix A, I mean this augment matrix, or to the given system of linear equation. So, and then this is the first step in the Gauss elimination method. And second step is reduce into row echelon form by applying elementary row operations. And finally, last step is, so of course, when we are reducing this augmented A into row echelon form, so we will get some another matrix. So if I call that, so let's say that row echelon form is this one. So that will be also one augmenting matrix. That means because we are just appending to A and B matrix here. So after applying the elementary operation, also we are going to get one matrix, and row echelon form will be also this type, C augmentation bar D. So then after reducing this given augmented matrix into row echelon form that I'm calling C augmented bar D, I mean this augmenting matrix, then what we have to do, write down the corresponding, the system corresponding to the augmenting matrix C augmenting bar D. So in brief, what is the steps basically? First of all, we have to write down or we have to construct the augmenting matrix, and so that can be obtained just augmenting that B matrix with A and just separating those matrix with augmentation bar. After that, we will apply elementary row operation to get the row echelon form of this augmenting matrix A augmenting bar B. And suppose that row echelon matrix is C augmentation bar D, then you need to write the corresponding system of linear equation to this augmenting matrix, which is the basically row echelon form of the given augmenting matrix A augmentation bar B. And because of the theorem, just a previous theorem, because we are just applying the elementary row operation, so whatever the row echelon form we will obtain, that will be the basically row equivalent to the given matrix, right? That exactly meaning that when we apply the elementary row operation, so we get some row equivalent form or row equivalent matrix. So A augmentation bar B and C augmentation bar D both are equivalent matrix. So by previous theorem, what we should have that both have same solution set. That means if we want to solve this given system of linear equation, so just x equal to b, then just solve the system of linear equation corresponding to this augmentation matrix C augmentation bar D. That means solve the system Cx equal to D using the back substitution. So this is actually our last step. Also, you can Cx equal to D using back substitution. So solve this system Cx equal to D using back substitution. And then whatever the solution we will obtain, that will be exactly the solution for the given system of linear equation. This is what theorem says. So, and also same time, let me also write here, because there is no much difference between Gauss-Jordan method and this Gauss elimination method. Right, and I'm not saying row equivalent or column equivalent, but I'm talking about the row equivalent only. That means when we will reduce some matrix into some different system of linear equation, or you can say suppose A is this coefficient matrix of given system of linear equation is A. Then if you reduce this matrix into another form, then we will just use only elementary row operations. That thing keep in mind here. So because all the things we are just talking about the row equivalence. We are not talking about at all the column equivalent, and column equivalent is also one concept, but we don't basically talk about here that column equivalence. Okay, so whenever I'm saying that two systems are equivalent, just applying the operations, so I'm just talking about the elementary row operations, nothing else.
Hello, sir.
Yeah.
सर अगर ये वैल्यू x1 x2 की वैल्यू अगर इसमें इक्वेशन में पुट करेंगे तो सर ये तो इसको सेटिस्फाई नहीं करेगी.
Sorry.
सर x1 x2 x3 और x4 की वैल्यू है ना.
Yeah.
तो सर ऊपर इक्वेशन में पुट अप करेंगे तो सर ये तो इनको सेटिस्फाई नहीं करेगी.
In which equation you are putting these values?
ये सर ये ऊपर रही
This
इक्वेशन
one.
में. Yes sir.
This is the different system of linear equation. I am saying that this is the one more we have. This is the system of linear equation, which is also simpler to solve the or to find the solution. And this is the another system of linear equation I'm considering, which is the basically where the coefficient matrix is simply diagonal matrix. So this system of linear equation and this system of linear equation are different. Okay, so you can just take this is one example. Okay, so this system of linear equation and this system of linear equation are different. I'm just trying to explain here that when we have some simple system of linear equation, then we can find a solution easily. So if you have this type system of linear equation, so in this case actually what? In this case, we have coefficient matrix is upper triangular matrix. So when we have coefficient matrix is upper triangular matrix, so we can find the solution using the Vex substitution. And when we have simply the coefficient matrix is simply diagonal matrix, so you can find the solution directly, just equating the just writing the corresponding system of linear equation. Then from the first equation you can find the x1, from the second equation you can find the x2, from the third equation we can find x3, and from the last equation we can find the x4. So these system of linear equations are different. Okay.
Yes sir.
So don't say that this is not satisfying something. Okay, so now let me state one